Good day, I'm Dr. T and welcome to my office. So when looking at molecules, one thing we want to look at quite often is shape. This is going to be particularly important in certain systems like those involving enzymes, in which the interaction with other molecules are going to be governed heavily by the shape of the molecule doing the interacting. Now, to look at shape and be able to predict what shapes we're going to have, there's a couple of approaches to take. The two dominant ones are what's known as valence shell electron pair repulsion theory, or VESPER. In this case, we are going to be looking at the pairs of electrons, those forming lone pairs or those in bonds, and looking at how they could get as far away from each other as possible. They're all negatively charged, and negatively charged things want to be as far away from other negatively charged things as possible, but still stay close to that wonderful positively charged nucleus. The other theory that we're going to be looking at is hybrid orbital theory. In this case, we're looking at the mathematical regions around the nucleus in which the electrons can hang out at. When we talked about them earlier, we were talking about things such as s, p, d, and f orbitals. But those orbitals assume that the atom is all by itself, completely unaffected by other atoms. Obviously, if you're in a molecule, you're not by yourself. So what we're doing is recalculating those orbitals, and doing so in a hybrid fashion. The mathematics that allows us to calculate the presence of an s or p orbital also allows us to calculate the presence of orbitals that have been blended together and forming new orbitals. Now, to start going through this, let's start with the simplest ones and then expand out to the more and more complicated shapes. Before I do this, though, I should point out that there are two different types of shapes. What we call electron domain geometry is really the simplest. This is looking at the shape with respect to lone pairs and bonds together. Just the electrons. The alternative is molecular domain geometry. In this case, we are looking at only the bonded pairs. This creates a little bit more of an interesting scenario because the lone pairs are still there. They're still changing the shape, but now we have the same shapes as the electron domain geometry, but missing legs because those are lone pairs and not bonds. Well, let's start in with the simplest one. So with three atoms, of course, if you only have two atoms, you're immediately linear. There's just nothing else going on. So with three atoms, presumably two electron domains, or I should say two electron domains, presumably three atoms, you really can form one shape, and that is going to be linear. Those two pairs of electrons are going to try and get as far away from each other as possible, and that's on the other side of the nucleus, and so they do this. Now, if this is looking at it in hybrid orbital theory, in this case we would then say, hey, this is the combination of two orbitals, an s orbital and a p orbital, or what we call sp hybridization. There are still two p orbitals that can interact, but not in a hybrid way, and generally speaking, not doing a linear face-on approach. They'll be interacting with what's known as a pi bond. The sp orbitals, though, will be interacting with what's known as a sigma bond and will directly overlap with the orbitals of the other attached atom. The pi bonds don't directly overlap. They overlap more on the sides. Okay, that's it for just two electron domains. Let's kick this up to three. Three electron domains will form a triangle, what we call trigonal planar. We call it planar because it's flat. There's no reason trying to go up. You're simply going to be closer to each other. In this case, each electron domain is going to be 120 degrees away from each other. This, for hybrid orbital theory, is known as sp2, one s and two p's. We still have one p orbital left over to do pi bonds, but two p orbitals and one of our s orbitals have been hybridized together to allow us to do sigma bonds. Now, at this point, we can have two different molecular domain geometries. We can have trigonal planar, assuming I have a central atom surrounded by three other atoms. Alternatively, though, if one of those three is actually a lone pair, then I can form a shape known as bent. In this case, the distance between the two bonds will actually be slightly less than 120 degrees because lone pairs tend to spread out and take a bit more space than bonded pairs do. but otherwise we'll get those two choices. Okay, so 4 electron domains brings a little bit more interest going on in this scenario. In this case, the electron domain geometry is going to be a tetrahedron. There are 4 pairs of electrons that are trying to get as far away from each other as possible. This doesn't form a square. Squares are only 2 dimensionals. With a tetrahedron, we're going into the 3rd dimension, allowing us to form something that's roughly the shape of a cattle trot, if you're familiar with those from medieval history. Angles will be 109.5 between each of the electron domains, as far apart as they can get. Now, with molecular domain geometry, we can get a couple interesting ones. Of course, you can have a tetrahedron. That's actually very common. Carbon particularly likes to do this. The presence of a lone pair, though, will start changing this. So nitrogen typically has a lone pair, and a single lone pair on your tetrahedron electron domain geometry will give a molecular domain geometry of a trigonal pyramid, or trigonal pyramidal. This looks like a triangle-shaped pyramid, so a triangle of triangles kind of scenario. If there are 2 lone pairs, then we are also resulting in bent, with an angle that is noticeably less than 109.5. You're actually probably closer to about 104.5 degrees, because, as I mentioned earlier, those lone pairs do tend to take up a little bit more space. When looking at this in hybrid orbital theory, we call this sp3. There are the 1 s orbital and 3 p orbitals hybridizing together to form the structure for this particular shape. In this case, it's going to, generally speaking, be all sigma bonds, no pi's. Elements in period 2 can't go beyond the aforementioned shapes because they don't have the ability to exceed 4 orbitals in their valence shell. However, elements in groups 3 and below have d orbitals in their valence shell that they can utilize. If you incorporate 1 d orbital, so what we call sp3d, then you can have 5 electron pairs in your electron pair geometry in what we call trigonal bipyramidal. It looks like a trigonal pyramid on top of a trigonal pyramid, so kind of this weird diamond shape. Now, of course, this gives us a few options for removing bonds and replacing them with lone pairs. So, of course, if I have 5 atoms attached, then this is going to be a trigonal pyramidal. Around the equator, it will have 120-degree bonds, and the 2 axial ones will be at 90 degrees compared to the equator, as one would expect. Typically, the lone pairs, because they are somewhat larger, will prefer to go towards the equator. So we're going to have a couple of shapes. If there's 1 lone pair, then we're going to reach seesaw. If you look at most pictures, you kind of turn it so the axis is going sideways, and then it actually looks like a teeter-totter, you know, the thing you did like this with as a kid. Or a seesaw. Yay. Remove 2 bonds and replace them with lone pairs. So now I have 3 bonds and 2 lone pairs. My molecular geometry is known as a T shape because it looks like the letter T. Once again, turn it 90 degrees so the axis is horizontal. It looks like the letter T. Finally, 3 lone pairs. Now all of a sudden, all I have left is the axis. I have a linear shape again. The last electron domain geometry that I'd like to talk about is the octahedral. In this case, I have 6 electron pairs, and I'm incorporating 2 d orbitals. So this is going to be sp3d2. Yay, this is a lot of electrons. And this is generally about as big and complicated as things get. Presumably you could go for more d orbitals, but you're just running out of room around the atom. It's just getting too crowded. So this looks like an octahedron, basically a square pyramid on top of a square pyramid kind of scenario for your shape. A D8 if you're a D&D fan. Now, if we start removing bonds and replacing with lone pairs, removing 1 is going to give you a square pyramid. Square bottom, and then a point. So think pyramids of Giza. Removing 2, and you're going to get square planar. The second lone pair typically prefers to be on the opposite side of the other. Then remove 3, and you're going to get a T-shape again, although basically the same T-shape. It's a slightly different cousin with more electrons, but it still is T-shape. And finally, take out 4 bonds and replace them with lone pairs, and you are looking at linear. Yay! This is the core of the shapes. Unfortunately, a fair amount of memorization, so I will let you have to that, and have a wonderful day.